Okay, good morning, everyone. Welcome to our Friday seminar series. Today, we are pleased to invite Dr. Gao from Canadian Geological Survey to give us a talk on the subject, Injection-Induced Earthquake in Canada, how research is transformed into regulation. And Dr. Gao got his bachelor degree in geophysics from the National Central University of Taiwan and a PhD in geophysics from the University of Illinois at Urbana-Champaign. Immediately after finishing his PhD, he was appointed as an assistant research fellow at the Institute of Earth Science, Academia Sinica of Taiwan. In his early career stage, he was in charge of establishing the broadband array in Taiwan for seismology. During his research career in Taiwan, he was a two-time recipient of the Outstanding Research Award of the National Research Council of Taiwan. Wow, that's a long title. And in 2002, he joined the Canadian Geological Survey as a research scientist working on earthquake source characteristics and seismogenic structures. He also served as an editorial member of several top-notch journals, such as the Journal of Geophysical Research. In 2019, he received a Departmental Achievement Award from the Natural Resources Canada, which is the equivalent version of the Department of Energy in Canada, for impact and contribution to excellence in science. Currently, he is the leader of the Induced Seismicity Research Project of the Department of Natural Resources of the Federal Government of Canada. Whew, long title. Anyhow, let's welcome Dr. Gao for this talk. Dr. Gao, take it away.
Okay, Dino, Dr. Gao, just a minute. Dino, thank you for the introduction. I would like personally to thank Dr. Gao on behalf of TechNet and CISOR. Dr. Gao has been very supportive of TechNet. He actually was part of one of the members of the TechNet review that we did last year, and his feedback is really very much appreciated. As Dino said, Dr. Gao is a coordinator of the Induced Seismicity project in Canada. So we're all looking forward to hear what you have to say to the group. Thank you again.
Sure. Thank you. Yeah, it is certainly my pleasure to be able to be here and share my learning and my experience in terms of induced seismicity research. And I certainly would like to thank Dino for giving me this opportunity. As we all know, the subject of induced seismicity is actually a very, very important topic, especially nowadays. It is not only related to the development of unconventional hydrocarbon resources, but also it actually has greatly improved our understanding of earthquakes. And I have to admit that because of this very important topic, the research science out of this particular topic has been so overwhelming in recent years that almost every one of us will not be able to catch up. And that certainly is the case today as well. So in today's talk, I'm not so much going to focus on the science or research or technical results of our program, which is probably another topic that I would like to introduce later on if I have the other opportunity. But rather, I like to focus on a topic that's probably very much related to government research agencies, and certainly that probably include BEG. That is how we actually, being a government research scientist, how do we actually transform our research results into regulation so that we can improve our government's operation? That's actually the sort of the fundamental importance of government research. So that's the title, and that's pretty much the focus of my talk. And as I said, there are a lot of science that's behind it that I won't be able to talk in detail. And I welcome the opportunity if you want to have further discussion with me on all those topics. So this is today's outline for my talk. I will briefly describe the unconventional hydrocarbon resources and the injection-induced earthquakes in Canada. And then I will introduce you the NRCan's, which is Natural Resources Canada's Induced Seismicity Research Project, in which I am the leader. I will describe the objectives and the strategies and our work plans behind this project. I will then focus mainly on how the collaboration with regulatory agencies and the industries and the academia and so on were put together, and how we actually linked the research results with the regulatory agencies so that it becomes the regulation for the industry. And to conclude my talk, I point out some of the points that I think how we should move forward from this point. This is, before we can start our discussion today, of course, we need to understand how many different types of injection-induced earthquakes we have. And I think for those of you, you probably are very familiar with most of them. So I'm going to fly this through very quickly. And the first kind of injection-induced earthquakes, which are also the one that cause most major damages, are the induced events due to wastewater injection, and sometimes we call wastewater disposal. And the injection rate can vary quite a bit. You know, they can be as small as 25,000 cubic meter per month to as high as 75,000 cubic meter per day. And just to be comparison, one Olympic swimming pool is about 2,500 cubic meter. So the injection amount that we are talking about here is extremely large. And also the operation time can vary from decades, from years to decades. It really depends. And the second type is the induced events due to hydraulic fracturing. And we all know that for hydraulic fracturing, they can, for now, it has been proved that they can cause earthquakes. Typical hydraulic fracturing well depth is about 1 to 3 kilometers. Each of the drilling well usually will have multiple drilling pad will have multiple horizontal drilling wells, and each of these drilling wells usually will host 5 to 20 fracking stages. And the injection pressure is very high. We're talking about 45 to 65 megapascal, and each stage use about 4,000 cubic meters of water plus 2,000 tons of sand. So the amount of water and the resources used in hydraulic fracturing is enormous. And of course, we also have other kind of injection-induced events, including enhanced oil and gas recovery, as well as those enhanced geothermal systems. The last one is mainly in Europe. I don't think here in North America we actually, or certainly in Canada, we don't have any EGS systems yet. Many people think that induced earthquakes is only happening recently, but I think that's definitely wrong, because here in Canada, the induced earthquakes actually happened as early as 1980s. That's mainly related to enhanced oil recovery operation in the Fort St. John area. And the operation, the enhanced injection happens early in 1980 and 1985 in different parts of the Fort St. John area. As I shown here in the on the map, this is a map adapted by Horner and others in 1994. The production rate actually declined in late 80s, and the local seismicity actually increased about 4 to 6 years later, comparing to the initiation of the injection. And the largest magnitude was magnitude 4.3 here. And the highest intensity was 5, which is characterized as moderate shaking according to modified Mercalli intensity scale. So Bob Horner actually conclude that the fault area were as large as 2,000 square meters, and therefore the hazard presented by this particular seismicity still needs to be adequately assessed. But after that, the injection declined, and essentially no induced earthquakes ever happened there anymore. So this topic sort of disappeared naturally. And we all know that the unconventional oil and gas development in North America becomes so important that it actually replaced the conventional way of our extraction of the hydrocarbon resources. Here in Canada, our unconventional oil and gas distribution is mainly in three places. One is the Western Canada Sedimentary Basin, which is here, including the BC and Alberta. The other one is the Maritime Basin, which is this one in East Canada. And the third one is the St. Lawrence platform that is mainly inside Quebec. In terms of seismicity, the majority part of earthquakes in Canada happened in two places. One is along the West Coast, which is the Cascadia subduction zone. That's also related to the subduction system along the Alaska and the collision in the Yakutat. The other part of the major seismicity is the East Canada that's mainly associated with the Gulf of St. Lawrence Valley here. But if you notice the difference between 2007 and 2017 is that, in fact, we can see a lot of these earthquakes that happened in the middle part of the British Columbia and Western Alberta, and that's this part. So these are the mainly induced earthquakes that we are going to focus today. In terms of the hydraulic fracturing induced earthquakes here in Canada, I compiled a list of major events that actually triggered all the regulatory changes. So starting about 2010, we had the first significant event that actually caught everybody's attention, which is a 3.6 earthquake happened in Home River Basin. Home River Basin is actually located right here. And then it followed, and it has another 3.6 earthquake in the next year, 2011 here. That actually basically triggered all the induced earthquake research here in Canada. In 2013, we had a magnitude 4.2 earthquake that happened in Fort St. John area, which is there. Then the magnitude starts to rise from 4.2 to 4.5, which is actually happened here. Then the Fox Creek events happened, which actually is the one that triggered the regulatory changes in Alberta in 2015. And then we have the magnitude 4.6. That's the largest one, both in Fox Creek and in Monterey. Here is the northern Monterey. And essentially the maximum magnitude of fracking-induced earthquakes stay at that level ever since. We have the latest one that happens in Red Deer area, which is actually further east. That's the latest one in West Canada. But if you look at from a government's point of view, you know, the priorities of the government actually can be very complicated. On one hand, the government really want a very successful resource development. And this is mainly because resource development can contribute directly to economic growth. So here we are talking about shale gas, tight oil, enhanced recovery, and so on and so on. These are mainly contribute to the economic benefit of the industry. On the other hand, government also have to really take care of the public safety and the protection of the environment. And both, quite often, the induced seismicity is exactly the place where these two overlap. On one hand, if you emphasize too much on the resources development, it will actually compromise the public safety. On the other hand, if you emphasize too much on public safety, then you will actually damage the resource development. How do we actually take care of both is a very balanced task. And induced seismicity is a typical example how we want to do that. Now, before we know how we want to do it, we have to realize what is the regulator's key concern. So the regulator's key concern, first of all, is that the earthquake's location, depth, and magnitude is something that they really want to know. If anything happened and is considered to be induced, this is the first thing they want to know. Then, of course, that involves the monitoring of the events and the uncertainty of the events. And in terms of seismic risk, they really want to know how we can assess that more accurately. So we want to know the ground motion prediction equation, and we also want to know what is the site amplification factor. So these are the things that the regulators want to know before they can have a good assessment of the seismic risk. And also they want to know the mitigation of the seismic risk. How do we mitigate the risk if we know they exist? So there are two ways of doing it. The passive way is that we establish some sort of traffic light protocol so that if something happens, we can immediately take reaction to reduce the risk. There are other ways to actually proactively reduce the risk. For example, if we can understand the controlling factors of these events, then we can design the model to make it less likely to happen. And of course, the public relationship and social license is actually important consideration from the regulator's point of view as well. So the NR can realize the importance of this issue, and we established a shale-gas research project with a focus on induced seismicity activity back in 2012. And the purpose of this project is to make a coordinated effort involving both public and private sectors to address the critical knowledge gaps in induced seismicity that's related to the unconventional oil and gas development. In 2016, the induced seismicity research activity was expanded to induced seismicity research project to cover all types of induced earthquakes that include hydraulic fracturing, wastewater disposal, enhanced recovery, CO2 sequestration, as well as the reservoir impoundance. The project strategy are threefolded. First, we want to have a national scope. We don't want this project to focus on just one area of a particular province. So for Western Canada and Eastern and North Canada, the scope is that we may have to do different things. For West Canada, we focus on targeted studies of significant events. Whereas in East and North, the fracking operation are not really very widespread yet. So the focus is to establish baselines of background seismicity in preparation for future development just in case. The approach is, it has two particular strategy. One is that we want to have collaboration with regulators and provincial and local governments, industry, and as well as the academia, so that we actually make a coordinated effort without spending the resources on the exact same thing. We also have to take a multidisciplinary approach, including seismology, geodesy, hydrology, and geomechanics, so that we can have a holistic understanding of the problem. And finally, in terms of the key plans, we want to establish and enhance the observational and or real-time monitoring capacity. This is mainly in work with the regulators. And we also want to develop an innovative methodology to improve the observation. And finally, we want to enhance the regulatory performances so that the balance between economic development and the public safety will be achieved. In terms of the national scope, we have various parts of Canada where we have established our tasks. So this is just a map of showing all these places in East and West Canada. I don't have time to go into detail of it, but basically it's important to maintain a national scope for a project like this. Of course, we installed a lot of news stations to increase our monitoring capacity. These are the photos photos of the stations that we set up in the northern part of British Columbia. First of all, we use the screw piling to go through the musket there so that the background noise can be minimized as much as possible. Because of the weather, we have extra number of solar panels to provide the necessary power and a very big battery pack. And we also have the post-hole installation to reduce the overall noise level. In terms of improving the regional earthquake monitoring, this is actually a plot of seismic stations we have over the years. As you can see, this is the distribution of seismic stations back in the year of 2013, and we have only a couple of stations in the places where the fracking was happening. So Natural Resources Canada worked very closely with the provincial regulators to come up, as well as the industry, to come up with a plan to densify our seismic stations in the area. So in 2015, we already established a fairly nice framework of backbone seismic stations in Northeast British Columbia and Western Alberta. And then we continue densified the stations in the VR basin here, as well as these arrays that we want to focus on the particular areas. And in 2019, we also established 2 more dense array right in this area where we have the most number of fracking wells. The seismic observation certainly will need help from the regulator in terms of getting their operational database. So we have worked very closely with BC Oil and Gas Commission to get their completion reports. And that turns out to be a critical database in order for us to work out the regulatory performance improvement. So this is actually an example that I want to show. For example, if you look at what happens back in 2006 and 2007, there were very little seismic earthquakes happen. This is during hydraulic fracturing. This is post hydraulic fracturing. Essentially, all earthquakes are very sparse. In 2010 and 2011, this is during hydraulic fracturing, and that circle is the hydraulic fracturing area. So you can see a lot of earthquakes happen there. And post hydraulic fracturing period was very mild. And that happens continuously for 2 years. So we have done careful review of these seismicities, and we conclude that the hydraulic fracturing can be responsible for significant induced earthquakes in Horn River Basin. And that actually initiated the first regulatory response to science. So back in 2012 and 2013, new permit conditions for drilling and production operation in Home River Basin was announced by BC Oil and Gas Commission. They specify the shutdown protocol and require microseismicity monitoring. We also try to come up with innovative methods to improve our detection, which is a topic that's very wide, and I don't really intend to go into any detail of them. I just want to mention that we have multiple new methods that we developed over the years to improve the automatic monitoring of the small events, to precisely determine the depth determination, and to effectively recognize the repeating events. All these three methods are already, this is already published. These two are in revision, which I think will be published very soon. But anyway, that's the way we try to improve our observation. And if you are interested in any of this, feel free to contact me. I'm more than happy to have further discussion with you on that. With that, we actually go study the entire Western Canada to see where the earthquakes, the induced earthquakes happened. And we noticed that they actually occurred in clusters in British Columbia and in Alberta, whereas the injection actually is very widespread. So if you look at the injection, it is almost everywhere. But if you look at the seismicity, it's actually very focused in clusters. So if you put these two together, we recognize a induced seismicity band here. That's where the majority of the induced earthquake happened. And in fact, if you even look carefully, they have, even within this band, they have clusters that has the highest number of events. So if you look at the spatial pattern of the induced earthquakes over years, you can see from 13 to 16 to 18, the pattern actually changed quite a bit. And that actually happens as well with respect to the injection. So this is the injection well distribution. As you can see, it becomes much less in 2018, and therefore the number of earthquakes become much less, but it becomes very focused in areas. So we noticed that they actually occurred very focused in clusters, and only a very small fraction of the induced events, fracking wells caused the events, and the real-time monitoring of small events becomes very necessary for regulator. So the next part is with all the results that we derived in terms of the seismic pattern, there are more regulatory responses to science. In 2015, the BC Oil and Gas, the BC government actually announced the new regulation on induced earthquakes. Specifically, they add a section 21.1 to the Drilling and Production Regulation of the Oil and Gas Activity Act. And that will suspend the operation if the earthquake occurred with magnitude larger than 4. In 2015, the induced earthquakes, induced seismicity tripartite protocol was announced. And this is through the Subsurface Order number 2 issued by Alberta Energy Regulator. And then in 2017, the BC government actually amended the drilling and production regulation to include all injection operations. And in 2019, the Alberta Energy Regulator issued another subsurface order to impose an even stronger tripartite protocol for the Red Deer area. And then there are also mandatory on-site induced seismicity monitoring. In 2016, the new permit condition was required for any new fracking operation to have the ground motion monitoring. So they have to deploy at least one Class A strong motion sensor within 3 kilometers of the drilling pad. They are required to monitor the entire drilling during the entire fracking operation, and they have to report if the ground motion is stronger than 0.008 G. Back in 2018, there were also new orders on monitoring, mitigation, and reporting requirement for permits holders in the Saskatchewan area, which is the area that I just shown with a lot of induced earthquakes. And in this case, they actually indicate that the suspension level becomes lower. If you have a magnitude 3 events instead of 4, you will have to suspend the operation. And also there are mitigation plans, they are required, as well as if anything happens with magnitude 1.5, they have to inform the regulator. There are also a scientific hydraulic fracturing review panel, which issued a final report in 2019. And this final report actually has 4 main sections: water quality, water quantity, induced seismicity, and fugitive emission. I don't have time to go through the detail of this report, but it's online available, so you are more than welcome to download a copy. And this review panel report actually provides a very important summary of scientific findings and recommendations, and that actually guide the government's effort toward improvement. So here, I'm going to show you one final example that how research can improve the regulation. In one of the big issues that's identified by the hydraulic fracturing review panel report is that there is a very significant magnitude discrepancy. The NRCan reported magnitude are systematically larger than those reported by local operators, because as we realize, the operators are required to put out dense arrays. So they actually have the capability to locate earthquakes and their magnitude. But they systematically complain that the values are smaller than NRCan reported. And this becomes an issue because the regulator will have to decide whether or not to shut down the operation based on the magnitude. So here, I show you a map. This is a compilation of the magnitudes determined by different stations at different distances for the same event. So this is the 2015 August 17 event, which, as you can see, if you have a station that's farther and farther away from the epicenter, you have a larger and larger magnitude. And that's a very disturbing problem. And this is mainly because the distance correction is inadequate for events in this area, so that the distance becomes a factor in your determination. And therefore, we actually initiated a research project trying to figure out what's going on. Essentially, what we found is that we can adequately account for the distance correction using a new formula. So this is our new formula that you can use to derive the distance adjustment factor, and that can actually change minimize the discrepancy so that you get a much better consistent magnitude value from stations both close to the epicenter and far away from the epicenter. From this map, you can see that in terms of the distance, if you get to, say, distance away from 2 kilometers, for example, starting from here, the value becomes very consistent. And certainly, if you look at the different events that we are looking at, there seems to have no particular bias toward the magnitude. So we found a very adequate formula that can be used for both the industry and the regulator to decide the magnitude without the discrepancy. And therefore, the next regulatory adjustment that we know is that the BC Oil and Gas Commission has already decided to adapt the new magnitude formula. So in their future regulatory decision process, and this is actually in response to one of the recommendations made by the hydraulic fracturing review panel report. And as soon as this kind of intention was out, the responses from the industry have been overwhelmingly positive. They really like that we try to minimize the discrepancy between the NRK magnitudes and their magnitudes. And also, the BC Oil and Gas Commission is now currently consulting with NRK, the Alberta Energy Regulator, and other government agencies on how to best move forward on this particular issue. So, with the remaining a couple of minutes, I'd like to look forward. I think looking forward, first of all, we must really keep improving our observation. After all, high resolution seismic data set for smaller signals, especially for those pre, co, and post seismic events, I think those are very important as far as the determination of the precise source characteristics are concerned. And we also need to have a complete database of accurate injection operation parameters. And certainly this will require collaboration from the regulator as well as the industry. We also need to have detailed 3D velocity structure because we really want to know not only the pre-existing faults, but also detect as many blind faults as possible. And certainly there are a lot of subsurface topographic features that may become the factor causing induced events. Another thing that as far as that we can look forward is that we should have targeted and focused the research on key issues. Now, as I said, I didn't actually have time to go over this research part, but the source characteristics are certainly very important because we want to know not only the distribution of the seismicity, but we also want to know their mechanisms, their stress drop, their rupture dimensions, and their slip history. And the reason that we understand all this is that then we can have a good understanding of the numerical part, the geomechanical behavior, as well as the controlling factors. So we want to be able to based on the seismic observation, to come up with a good understanding of the geomechanics behind it, so that we have a realistic geological, hydrological, and injection conditions to simulate the seismogenic process. The delineation of the controlling factors, again, has to be based on the seismic observation. But once we understand these controlling factors, then we can take a very proactive way to do it. And there are several ways of doing it. Artificial intelligence now is very hot, and we are actually doing it right now. But there are also other ways that we want to explore. And finally, we have to really thinking about the effective and balanced regulations. And this is really from the regulator's point of view, this is the most important thing. We have to recognize the geographic as well as the regional differences. For example, different tectonic strain rate will give you different rate of induced seismicity, and that has to be, that should be considered in the regulatory framework. There are the numbers of injection wells and the amount of injection fluids are important. So you don't necessarily want to fit everything with one size shoes. And also the population density is another important concern. Here in British Columbia and and Alberta, it's already implemented that the different area with different population density, the threshold are very different. And we also want to have, move from the passive reactions to proactive measures. For example, we want to understand what is the actual ground shaking with respect to the magnitude. Because given the same magnitude, if the ground shaking level is different, you may have a very small event and yet the ground amplification factor is large and therefore the ground shaking has become larger, so on. we also want to set up certain prohibited zones where no injection can be allowed whatsoever. And this is something that you have to be very careful because there are not only economic consequences, but also legal consequences. And finally, the model-based prediction is very important because with the model-based prediction, we will be able to assess short-term seismic hazards, and that can precisely determine how you want to design your operation. And there are also physical models of injection and structure interaction that you want to be able to avoid a certain area or certain situation so that we know we can minimize the chance of inducing any earthquakes. With that, I think I will stop at this point. So if you have any questions, I'd be more than happy to answer. Thank you.
Thank you, Dr. Gao. And we have 3 questions in line from one person. So Sayed, would you like to go ahead? Sayed?
I saw there is no question, so I posted a few questions in the chat, but
okay. Let's see.
But I can read through them, but I'm coming from the CCS side, and I noticed that most of the hydraulic, the induced seismicity that you were talking about is coming from hydraulic fracturing. I just wanted you to comment, what is the observations related to the saltwater disposal specifically and CCS, if any, observation has been there. And the next 2 question was, do you think is there going to be any differences on the regulatory side when it comes to the regulations to hydraulic fracturing versus, saltwater disposal or CCS? Is there going to be any differences, or how they're going to treat these 2 things differently?
Yes.
And also the last one was about the outreach. Have you guys done anything on the outreach side, or what are the plans for that?
Great, thank you. Yeah, I think the CCS, the carbon sequestration effort is certainly an important one here in Canada. This is the carbon sequestration site here in Canada that's already in operation for quite some time. This is the Equistore site in Saskatchewan, where they collect the carbon, the CO2 from a very large power plant and then inject it into it. I think it's in operation for many years. We have a monitoring seismic network on top of it for many years. And the result is that we have not found any sign of induced earthquakes there. So in terms of carbon sequestration operation there, it's actually very stable. Now, so that answers your first question. We haven't really seen any particular induced events that's associated with carbon sequestration. And in terms of regulation, indeed, the regulation are different. Right now, I think we realize that the hydraulic fracturing caused the majority part of induced earthquakes in Canada. So the regulation on hydraulic fracturing and wastewater disposal in British Columbia and Western Alberta are very dynamic. They constantly want to improve the regulation on that. The regulation on carbon sequestration so far has been very minimal because, as I said, the observation indicate that there is no particular concern as far as induced earthquakes is about. So the regulation indeed are different for different type of injections. And outreach is a very important topic. I think actually it's one of the most, as I point out in my regulators concern. The social license is a very important aspect. If we can't get the social license properly, then it's very difficult for the industry to move. So outreach usually is done collectively. Not only by the NRCan research scientists, but also by the Oil and Gas Commission and Alberta Energy Regulator. the industry itself, for example, the Canadian Association of Petroleum Producers, CAPP, they also started a very active outreach program, trying to get people understand what are behind the injections and so on. So I don't have time to go into the outreach part, but it is a very important part of the government research organization, as well as the regulatory organizations activities.
Thank you.
Okay, so next question is from Peter. Peter, you're up.
Yeah, good morning. Appreciate your talk. Thank you for visiting the BEG virtually. I'm coming from the geomechanics side. I was wondering if you could comment a little bit on what the role of geomechanics is in regulatory decision-making in Canada. How much is it involved? What kind of work is done routinely that would factor into the regulatory decision-making?
Yes, geomechanics, as I said, geomechanics is really the key component that you use to connect your seismic observation to your model. And right now, it looks like the regulatory trend is to move from passive regulation to proactive regulation. Now, in order for you to get a very effective proactive regulation, this is where your expertise will come in, because you will need a very nice prediction capability in order to predict based on the injection parameter. Not based on the seismic observation, because if seismic observation is already happened, based on your injection scenario, you want to predict what's going to happen, and therefore impose the regulation. So that's where the geomechanics will help. But I don't think we are there yet, because there are a lot of uncertainties and a lot of unknowns that we just cannot predict the scenario in a satisfactory way. Satisfactory meaning that we can use that in regulations, so that we can use that in regulation to avoid any legal actions. So that's actually how that's how government view it. You have to come up with a regulation that you don't cause a lot of legal trouble. So I don't think we are there yet, but certainly geomechanics is a very important part of the whole scenario, because once you want to move from passive regulation to proactive regulation, this is the way to go.
So I understand your answer to be primarily a forward-looking statement rather than what you're currently doing. Is that correct?
Yes. The current way, as far as I can see, is mainly on the research side. We have to do our research in order to really understand the geomechanical aspect of the induced seismicity process. Once you understand that, then you move from a passive way of regulation to proactive way of regulation, and that's how you actually contribute to the regulation. Sure.
It's just easier said than done. And what my experience is, some of the geomechanics is it's so much effort to do this rigorously for one location that by the time you want to have a response, by the time we have a response from the geomechanics, the interests of the operators and the regulators may have moved on and to different areas. So it's very site specific and a very tedious, slow process to do it rigorously. And if you do it fast and less rigorously, then the answer may not be satisfactory. So there's a bit of a technical challenge there.
I totally agree with you. I think, but my preference is that you should do that in a very nice, precise way, an accurate way, even though it's local at local sites. But I think the accumulated knowledge will help. So in that sense, once we accumulate enough of this knowledge, and collectively, it can become regulation.
Right. Yeah. Thank you so much.
The next one is from Alexandros. Go ahead.
Yeah, Dr. Carl, thank you again. As I said in the beginning, thank you again for your presentation. I think it was nice to have such a presentation for our group. I have a question that has to do with the time that you see no earthquakes after hydraulic fracturing. Is it just when the last job finishes, or is it during the process? Or if it is after the job finishes, is it how many, is it days or a week, is it weeks?
Okay. In general, what we have seen here is that when the seismic response happened, it is very quick to the hydraulic fracturing time. So generally speaking, when the hydraulic fracturing starts, if something is going to happen, it usually happens very quickly. We are talking about from hours to days. If something is going to happen, it will happen very quickly. If there's nothing happened during the first 1 week or 1.5 weeks, then usually nothing will happen followed. But the ending, however, is different. Sometimes you actually have the things happen, say, in the middle of the injection, and then, even though the operators adjust their operation, the events continues to happen even after they complete their injection. So that's the kind of example we have seen as well. There are a few examples where the entire operation has been completed. There's nothing you can do, and then 1 week later something happened. There are these kind of examples that we observed especially in Fox Creek. These are some very interesting cases that we are studying right now. We suspect that it's mainly due to the delay time that's associated with fluid migration. But anyhow, for the majority case, the response is very quick. We are talking about hours to days.
Yeah, that's very similar to what we see here in Texas. Actually, it's hours and days, and we tried also to see if we can have seismicity after 10 days from the end job. It usually doesn't go up to that long. It stops very promptly, actually.
Yeah, I'm glad to know that we are seeing the same thing.
The next one comes from Peter Hennis. Peter, please go ahead.
Thank you, Dino. My question is a follow-up to Peter Eichelbold's question regarding your comments on geomechanics. Geomechanics is a very broad thing,
right?
From very simple approaches to full physics computations that assess things like poroelasticity. So if you could be a little more specific about what you mean by geomechanics, because it could just be understanding stress and pore pressure, and when a fault might become sensitive just due to changes in pore fluid pressure, or it might involve more full physics approaches that I think was part of Peter Eichelbold's question. Where do that range of geomechanics analysis from fairly straightforward to fairly complex, where does that range fit in addressing regulation?
Okay, let me give you example. I think that will make my statement easier. For example, we know that in terms of how we actually activate the induced event, quite often people indicate that you increase the pore pressure and therefore you facilitate the event. Now, the other way is that you actually have a poroelastic effect that actually change the state of stress along the fault, and therefore you cause an earthquake. Now, either way, you require a nice, a good understanding of the system, the mechanical part of the system, in order to do a quantitative assessment. How much of the pore pressure is caused by the injection? How much of the poroelastic stress can be caused along the fault, and so on. So these are the kind of things that we know, that we can do. However, the other thing is that there are a number of examples of induced earthquakes where it seems like the poroelastic stress caused by injection, once you get away from the well, for a certain distance, the amount of the stress increase is so small that it becomes difficult for us to imagine that this small amount of stress can cause events, and therefore one of the research trend nowadays is to come up with different mechanism that you can somehow still trigger an earthquake that's several or tens of kilometers away from your injection well and still cause a significant shaking. One of the possible scenario is that you actually have a conduit, some sort of hydrological channel, that the fluids simply migrate very easily because of the high permeability, very easily into the fault system. The other way is that you can have a seismic rupture. That's because of the material property itself. For example, very high hydrocarbon content, that kind of thing. And therefore, the rupture is aseismic initially, and it somehow reached the site of the fault and becomes seismic. There are all kinds of different scenarios that people want to be able to explain this. But I think fundamentally, the amount of how you actually link the injection scenario to the stress state along a fault, that's what's missing. And I think that's the fundamental question that we want to be able to answer. And as far as I can see, geomechanical simulation is really the most straightforward way to answer that. But as I said, there are simple ways, there are complicated ways, there are all kinds of different approaches. And these kind of different approaches, really, I personally don't have any preference one way or the other. But I would suggest, and certainly it's my personal opinion, is that it really depends on the situation. We may have to develop specific customized approach to figure out what's the physics. My point is that once we understand the underlying physics that's governing all these different phenomena, then we can actually incorporate that into regulation. So the regulation usually is the very last step. You have to do it very incrementally to make sure that you don't over-regulate. That's what I say, over-regulate. And in the meantime, you don't want people to see that you are actually doing the industry a favor. So that's the balance. That's the balanced approach that we have to be very careful.
That was a great discussion. Thank you.
Our time is approaching 10 o'clock. So any quick question? Okay, if not, let's thank Dr. Gao again for his talk.
Thank you.
And the last one will be next Friday, our final serious talk for this academic year. So we'll be talked by Dr. Lin on the post-economics of the stage. So we are looking forward to it. Until then, thanks again. Have a nice weekend. Bye.
Bye. Thank you.